Hello everyone. In this clip, we are going to talk about finding the time period of SHM of simple pendulum. So, suppose we have a bob suspended by an inextensible string. The mass is m. So, what we have observed is this will undergo oscillations, a to and fro motion. So, it will come to its maximum amplitude, that is its extreme position. So in this case you have this angle, you have this angle. So from the mean position to the extreme position, the angular displacement is suppose alpha. So this alpha is very it is very large. So in this case, in this scenario of finding time period, we have to take a very small displacement. What we have to do is we have to just hold this bob, we have to just displace a little bit, like I'm drawing here. We have to bring it to a very small displacement, like let it be theta, so that when we release it, it will undergo oscillations with a very small amplitude. This theta will be very small. This theta is very small. So this theta will be very small, so due to which it will undergo oscillations of very small, extremely small amplitude, and we will consider those oscillations and we will try to bring them in form of SHM, like we will try to prove them as SHM. So I am drawing that case once again. So suppose you have this, you have a bob of mass m suspended. Now this is being displaced by an angle theta. So this is your mass m. So when this theta is very small, we have assumed it earlier. This is the limitation, this is the assumption that we have used. So we will now draw the forces. This is mg acting downwards due to the mass. Then you will have a force acting along the string, and you will have a force acting perpendicular. So when you extend it, you will find that this is theta. This angle is going to be theta. That is alternate interior angles. So if this is theta, this angle is going to be theta. This is vertically opposite angles. So this is mg. This component will turn out to be mg cos of theta, and this will be your mg sin theta. So now when you have displaced this, you will have a restoring torque acting, which will try to bring this bob back to its mean position. So you will have a restoring torque. So you will have torque restoring. So you will have some value. So now in rotation, you have studied that torque is equal to r cross f, torque vector. So magnitude of torque is rf sin theta. So in this in this situation, your magnitude of torque is rf sin theta. So here sin theta is 90 degree, because this r and this force is perpendicular to each other. So sine of 90 is 1, so you will have r into f. So your force is mg sin theta, and your r is this length. This length is L. So we can write mg sine of theta into L. I'm rubbing this part. This is your knowledge from rotational motion. Now what you have is, you also know from rotation that this torque is equal to I alpha, and this alpha will be the same acceleration of restoring force. So in this scenario where you have a string, you have a mass, so for this system you have I is equal to ml square, mass into length square. So we will use this data here. We will put this torque restoring is equal to I into alpha restoring, and we will put the value of I as ml square. So we are going to substitute this. So we have torque restoring is equal to I into alpha restoring is equal to mg sine theta into L. Now we will substitute this I, that is moment of inertia, as m L square alpha restoring is equal to mg sine theta into L. So here 1L get cancelled, m get cancelled. Your alpha r, that is your acceleration restoring, comes out to be g by L sine theta. So now, as we have assumed this theta to be very small, you must have studied this in limits. That is, this is your approximation that is used, everywhere in physics and also in maths. That if theta is very small, then sine of theta is nearly equal to tan of theta is nearly equal to theta. So we will replace the sine theta as theta. So we will have alpha r is equal to g by L into theta. So now one thing you must know, that in simple SHM, that is in your SHM in linear, you had acceleration directly proportional to x. You have acceleration is equal to minus of omega square x. In linear equation, you have acceleration directly proportional to x, and we have acceleration is equal to minus of omega square x, or you have mod of a is equal to omega square x. So this is in your simple. So when you talk about in rotation, that is in your rotational SHM, that this acceleration will be replaced by angular acceleration alpha. This your angular velocity will remain same, and this simple displacement will be replaced by angular displacement theta. So here what you can see, that this angular acceleration is directly proportional to theta. So then you have SHM. This is your requirement for SHM in rotation. So we are getting this, that this acceleration is coming out to be directly proportional to theta. So here we are getting SHM. So now, as we have related it as SHM, now we can replace this alpha r as minus omega square theta. We will not put this minus because we are taking its mod, that is its magnitude only. We are not concerned about direction now. So we'll put it as omega square theta. I hope you understood that how this omega square theta came, because in simple you were aware of acceleration is equal to minus omega square x. So when you talk about in terms of rotation, that is in your rotational mechanics, you must have learned that acceleration is your alpha, that is your angular acceleration, and in terms of rotation your displacement is theta, that is your angular theta. In these terms we study our rotational motion. So that is how we came to this point, that is omega square theta is your restoring acceleration. So this is equal to g by L theta. Theta get cancelled. Omega comes out to be under root of g by L. So your omega is 2 pi by t is equal to under root of g by L. So your t comes out to be 2 pi under root of L by g. So this is your time period of a simple pendulum. So you all knew this from, I think, your class 9th or 10th, but the derivation of it with the help of SHM is done in this video. Thank you very much. Hope you understood.